Today we are going to be learning about our scientific inquiry, what that actually means, and how we can apply these different ideas to science, not just physics. So the idea about physics is that, or in any science in general, is that we start with a problem and we work our way to finding a solution, what's causing the problem, why there's a problem in the first place, and what we can do to fix it potentially. So before we can begin with what physics actually means and working through actual physics, the first thing that we need to look at is what is science. Since physics is the most broad form, we need to know the definition of science and strengths and limitations that it has. This objective right here is going to be probably one of the most important in your scientific career. Is to distinguish between hypotheses and theories. You've probably heard a hypothesis is an educated guess. That's not exactly correct. And I'll go into kind of what a hypothesis actually truly means and how that does different from a theory. And when we're talking in normal conversation, for us, a lot of times these two get mixed up. But in science, it's a very clear distinction between the two. And then we're also going to explain the impact of the scientific contributions of historical and contemporary scientists on scientific thought and on society. So we're going to learn about some scientists and what they have offered to science as a whole. So our first question here for our to check to see if you learned anything about this lecture, is that you're able to define science. So right now, what I would like you to do is pause the video, and I would like for you to write your own definition of science before we talk about anything else. And then to also choose one of the choices here for number 2. You see an icicle hanging from a branch or roof and notice that the ice forms in ripples on the surface of the icicle. Which of the following is a valid way to test a hypothesis about these ripples? So take a second now and choose A, B, C, or D. Number 3, which of the following could be used as scientific evidence? Pause now and choose your answer. And just like what happened last week, we'll go over what the correct answers for these are. We can see if we had any development over time or if we already knew this. Also, what did Penzias and Wilson contribute to our understanding and origins of the universe? These guys are going to be important to us, specifically in physics. Take a second now. You definitely want to put these, if you're doing Cornell notes, you want to put these on your left-hand side because we will be defining them as we work through this lecture today. If you're doing any other kind of notes, once again, make sure that you're paying attention that we're going to go over hypothesis, theory, objectivity, repeatability, experiment, and scientific method. We're going to go over all of these. Now, scientific method has changed over time. So whenever we talk about it, I'll go into kind of how some things are different now. Especially when we're talking about high school science classes. We don't really do this scientific method much anymore, necessarily. It's more of a thought experiment as opposed to actually planning experiments now at your grade level. So the first thing, we want to get into what science actually is. And all sciences, the most broad definition is the study of the physical world. So the things that we see around us, the things that physically exist, that we know are there. And the National Academy of Sciences defines science as the use of evidence to construct testable explanations and predictions of natural phenomena, as well as the knowledge generated through this process. So it's basically a gathering of information from a test and then making predictions about what we see from that. Even if our test fails, we still gain some knowledge from that. So, a lot of times, whenever somebody says that they can't do something or they don't understand science, they don't fundamentally understand that with science comes failure. And learning through just the process of experimentation, whether it's right or wrong. You thought something was going to happen and it didn't. So, once again, this is kind of more definitions than we probably ever needed to know. We can use that definition of science to explain something like how the Earth is orbiting the sun. Now, we know that Earth does not stay still, but how do we know that? And how have they known that for so long? Well, physically, any type of modeling that would be done, we would see the Earth moving around the sun. Mathematically, we can look at different equations like the force of gravity and knowing what gravity is. And then conceptual models will be that the sun is surrounded by a gravitational force field, which we haven't got into yet, but we'll talk about them. So we have different models that we can even use to apply science and that knowledge. We use science because it's an explanation of the world around us, but we're always gaining more knowledge. We're always gaining more information. So at any time, we can change some of the things that we know to be true or what we think are true. An example of this would be some experiments that were done with hygiene. When I want to say it was in England, there were midwives who had a higher success in birth rates and less mother fatality. And so doctors were wondering, well, why are the doctors having more infant mortality, more mother fatality? Why are these people dying with the doctors who are trained to be doctors, and the midwives are more successful? So they did a bunch of different studies about how women who were the midwives, how they were delivering babies. Like the mother would lay on her side, and they saw that there was still the same amount of fatality with the doctors, and the midwives were still more successful. So they tested again and again and again until they actually watched the whole process of midwives helping women give birth, and they found that the midwives were washing their hands. So science is always flexible. We take the information that's given to us and we add it to everything that we already know. Everything is constantly being tested and revised in science. And as technology grows and develops, we're seeing that we're getting more information than we ever knew possible. For the longest time in atomic theory, it was that, atoms are made up of electrons, protons, and neutrons. Well, we found out that there's something even smaller called a quark. So we add information constantly as new technology is available, and we're learning more and more. But we are limited in science because it has to be physical and observable and testable. If it's not any of those things, then we're limited as far as science is concerned. So things like ghosts or things that just wouldn't physically happen in the natural world, we can't test. So that's why, we're limited in the sense that if we can't see it, we can't test it. And if we can't test it, we can't change what we know. So technology has helped us a lot with these limitations specifically. Physics is both a process and a body of knowledge. There are some things that are just going to exist in physics, and we know them to be true, like gravity. That is a natural law. We are going to see gravity happen. If you drop something, we know that it is going to fall to the ground or to the nearest surface and stay there. It's not going to just float. That is an example of knowledge. But the process is going through and gathering that information. Isaac Newton sitting under the apple tree and getting hit on the head with an apple and realizing that gravity exists. That was a process to get to that natural law, that body of knowledge. So our knowledge is going to include any facts. We know the mass of an electron, which is right here, 9.1 times 10 to the negative 31st kilograms. That is a very small amount. We know that electrons weigh that amount. The process is the scientific inquiry. How did we find out that the mass of the electron weighs that? So the process of proposing and testing potential explanations to discover which ones are true laws of nature is scientific inquiry. Those are going to be those questions that you have about your world around you, but then setting up the process of testing to gain that knowledge. So a scientist might find that when she shines a light on a mirror at an angle, the light always reflects from the mirror at the same angle. So it is, a reflective surface. This creates the law of reflection. If she tries this for different angles, she will discover that this is always true, that it will always be reflected back at the same angle. So the law of reflection was tested through shining a light in the mirror. A hypothesis is a tentative, testable explanation for observable physical phenomena. A lot of times, like I said, you'll hear this stated as an educated guess. I hate that. It is your best explanation for what you think is going to happen based on the life that you have lived thus far. It's not just a random, if I leave a plant in the dark, it's not going to grow. Well, why do you think that? Okay? This is where those CER statements come in handy. The if, then, because statements. So most hypotheses are typically incomplete when they are first proposed. For example, the earth is flat. You can say that, but it gives us no idea how you know that or how you can get to that conclusion. So hypotheses are still important because they provide something that can be tested and revised. So take a second now, and you can change flat to round, because flat earthers are odd. So take a second now and try to write a correct hypothesis for the earth is flat. Go ahead and pause the video. You definitely want to have an if, then, and because in there somewhere. So if the earth, or if whatever observable physical phenomena is happening, then the earth must be round, because providing some evidence and some context for that proposal that you are making. Now, how this is different from a theory is a comprehensive, well-established, highly reliable explanation of natural and physical phenomena. That means that a theory is our most well-established bit of information in science. For example, cell theory. Most of us have heard it's just a theory. Well, cell theory states that all living things are made up of cells. Atomic theory, everything that's matter is made up of atoms. Evolution is a theory, the fact that things will change over time. So when you hear it's just a theory, that's incorrect, because there has been test after test to prove this. The tests have been repeated. There's multiple lines of evidence that support that claim. And it's the most reasonable explanation that we can come up with based on what we know so far. So can theories be revised? Absolutely they can. It's rare. Mostly things just get added to theories. So how are these things different? So an example of this would be that Newton hypothesized that light is a particle that bounces off a surface like a billiard ball. So light will hit something and bounce back. is what this is saying. Then we had other people that are saying, I don't think it's a particle, but instead I think it's a wavelength. And the truth is that neither hypothesis is correct. Both were combined to form the modern quantum theory of light. So now we've taken some information that was done by Newton where we saw particles that were able to bounce. And then we saw times when light behaved like a wavelength. So neither one was correct, and that's okay. What happened is they actually got combined together. That light is both a particle and a wavelength because of the way that it behaves. So when you hear theory, that's somebody saying like it's a hunch. They suspect something. But remember that scientific theory is very well tested, well explained. And it has come up against some of the harshest criticisms. Think about evolution. Evolution is a theory, but even today we see a lot of times where some people say men do not come from monkeys, but they fundamentally lack the understanding of what evolution truly is. So evolution even has 5 different ways, 5 different pieces of evidence that support that, that it has existed and things have indeed changed over time. And these different evidence, these 5 pieces are constantly being added to because different people are adding to the experiments. They are repeating them. They are changing and kind of working through some different issues. But at the end of the day, anyone who tests this theory, a scientific theory, should observe the same results. And if they don't, then we need to go back and look to see if there was a mistake that was made. Because if we're changing a theory, we definitely need to know that whoever was doing the test is accurate. So the scientific method is that process of proposing theories and testing them. So you start with a hypothesis, and eventually it will only become a theory if it has been tested multiple times and the same conclusion is made about the hypothesis. So it's going to be repeated several times. It's going to be talked over several times. And so this will lead us into sort of our lab reports and why our record keeping is so important. So how does the scientific method work? The first begins with a question. Simple. What shape is the Earth and how do we get there? So the question is, what is the shape? Typically it'll be a what question. Your hypothesis can be what you observe. So I look outside and I don't see that the ground is rounded, so I'm going to say that the Earth is flat. And then from that we would make a prediction, what we think would happen. If I travel in a ship in one direction, then I will fall off the Earth's edge. That is how I'm going to test it. I predict that I will fall off. So I get in my ship and I sail in one direction and I keep going and I keep going and I keep going, and eventually I return to my starting point. I didn't fall off the edge. So from that, it would contradict that prediction. I would go back and change my hypothesis. I would say, okay, now I think the Earth is round because I went all the way around it and I ended up at the same starting point. Okay? From that, I would begin that same thing. I would travel in my ship in one direction. I say that now it's round. I'm not going to fall off the face of the Earth. I do the test. I sail. I go all the way around. I end up back at my starting point. So now I have reached a new conclusion. And that is the shape of the Earth is round. Okay? So doing this process, your hypothesis may be different than your conclusion. So obviously we said here that the Earth is flat. But by the end of that, we knew that it wasn't. That's okay. And I think that's where a lot of, especially high school students, struggle, is that it's okay to be wrong in science. You don't ever want to leave it with your conclusion being wrong, though. You want to go back to that hypothesis and prediction and think, okay, my conclusion didn't work out, so what must be true now? I revise that hypothesis, I make a new prediction, and then I test that prediction. Okay, so you see here that science is very cyclical. We go back and we test constantly. So, I want you now on your piece of paper, go ahead and letter A through G here, and I want you to tell me, is a theory tentative, is a hypothesis tentative, or are both tentative? Which is testable? Capable of being observed or supported by experimental evidence. Well established, highly reliable, based on natural physical phenomena, and subject to change. Tell me if that is any of these are a theory, hypotheses, or both. Go ahead and pause and answer those questions now. So a hypothesis is tentative, okay? So that means that we can change it, we can edit it. Both of them are going to be testable. It's just whether are we going to add to the body of evidence or are we going to create the body of evidence. Both are capable of being observed. Theories are well established. They've taken time. They have many tests supporting them. Highly reliable. Theories are also reliable. Based on natural physical phenomena, the things that we see and that we can test, both. And then subject to change. We can change theories. We can change hypotheses. So some scientists that are going to be really important and have an impact on our society. Remember that science is cyclical, so it's going in a cycle, and each scientist builds on the results of others until eventually we gain more and more information. So an example of this, in 1927, we have the proposition of the Big Bang Theory, that the universe came about from a giant explosion. And then Alpher and Herman predicted that the universe's temperature would be 5 Kelvin based on this theory. Then we build on their experiment that they have verified the predicted temperature. Penzias and Wilson did. And then finally, in 1992, Smoot and Mather measured variations in radiation that led to the present-day clusters of galaxies from the predicted temperature. So scientific theories are subject to change as new areas of science and new technologies are developed. So basically, everything starts as a general hypothesis. You know, we have the idea that there is the Big Bang Theory. There was evidence that supported that theory that the universe started as an explosion. Then we have additional testing being done that because we have this idea of the Big Bang Theory, we do know what the temperature of the universe may be. And then from that, we can verify that information, and then from that information we can measure radiation that will tell us that there are galaxies and there are clusters of them out there in the universe. Another example, a geological team found high concentrations of iridium in rock from the time of the dinosaur extinction. Only asteroids can ever have that much iridium. So the idea here was that the dinosaur extinction was caused by the impact from a giant asteroid, because we are finding that in the time of dinosaurs, there was something that is only in asteroids. Well, then an asteroid must have hit the Earth. And then from there, we can gain more and more information supporting this theory. Another example that we see as far as theory and then scientists building on the information, there was research about global temperature raises and changes and rising in sea levels. So they wanted to know why that was happening. How this impacts society is that we as humans are having a very large impact on Earth for a lot of different reasons. But when we're talking about climate change, we burn fossil fuels. When we burn fossil fuels, which are made up of carbon, in a combustion reaction, we are releasing carbon dioxide into the air. Carbon dioxide is great because it helps keep our planet warm and it exists out in the atmosphere already. But when we add massive amounts to it, we're trapping more and more heat, more of that light energy from the sun. And when we trap that, we are increasing temperatures, which is causing glaciers to melt. We see icebergs melting, which is raising sea levels, which is changing weather patterns, currents. It's changing the pH of the ocean, causing it to be more acidic. So science is important to society in a lot of ways. We build these scientific theories because we want to analyze and evaluate what's happening in the world around us. And then we can critique some of those explanations. A widely criticized experiment, for example, was whenever, it's probably been close to 15 years now, there was a study that was done that said vaccines cause autism, and that there was a correlation between the two. And because of that correlation, they discovered that there was causation. Well, when the experiment was repeated, because that's what we do in science, there was major errors in the scientific data that was collected. And because of those major errors, they found out that the experiment was a fraud, that the scientists who were conducting it were inputting fraudulent information. That's why we continue to retest. And that's why it's so important. And that's why our analysis of what happens is so important. And the most important part of science is saying that it's okay, I was wrong. My prediction was incorrect. But from that, we can gather still more information because it is a cycle. We would go back and say, okay, well, why was I wrong? So remember that whenever we are analyzing a scientific explanation, we want to see observational evidence, things that we can actually see. Their reasoning behind their explanation is logical. Why did they come to this conclusion? How did they get there? Okay, and we do want to see experimental testing, actual experiments being done, not just collecting Google information. That is not research. Doing research is actually doing the experiments to come to that logical conclusion based on the observational evidence that we see. Okay, so observational evidence, remember, things that we can see can be analyzed and evaluated. Observations of the phases of Venus support the explanation that both Earth and Venus orbit the sun. Okay, we can actually see Venus in the night sky, and we can see its changes throughout a year as we circle the sun. So, because of those that observation, we are making an assumption here that maybe this Earth moves around the sun too, because Venus does. So, these are objective, meaning that I don't have any skin in the game here necessarily. I am not trying to subjugate this to my will, to my beliefs, okay? I went into this open-minded. I can repeat this experiment again and again. I can watch those changes in Venus throughout another year. Somebody else could do that. An example of logical reasoning. The Earth actually does not sit straight up and down, but instead it has like a 23-degree tilt to it when we travel around the sun. So we see here on Earth as we rotate around the sun is that we have seasons. We have a summer and we have a winter. And that, our daylight changes. Okay? So is this something that we could assume that there is a tilt because we have these seasons, because we have summer, because we have winter, and because they are different in the northern and southern hemispheres? So as we're moving towards winter in the northern hemisphere, we will be here in fall. It is actually spring turning to summer in the southern hemisphere. So people like us people in Australia are experiencing winter temperatures. So logically, we can use this information. We can observe things like noontime in Austin, Texas. We would see that it would be 53 degrees from vertical in winter and at 7 degrees vertical in summer. So because of that, if it's at 30 degrees, we can add 23 to get 53, and we can subtract 23 from 30 and get 7. Okay, so we can make this fair reasoning because of the information that we gather. And it's logical. It makes sense. We can prove it with math. Experimental testing may be analyzed and evaluated through, or explanations can be analyzed and evaluated through scientific testing. A well-designed experiment allows you to change one variable to determine precisely how other variables respond. So one that I like to use because we see it, and some of us are good plant parents here. An example of this is I want to see how sunlight affects the growth of plants. Okay, so I would take one plant, put it in the sun, take one plant, put it in a closet. So one plant is getting sunlight, one is not. I would not also say, well, I want to see how water affects plant growth at the same time, where I would water one plant and not water one plant. Because if I see growth because of sunlight, and that's the plant I chose not to water, well, is it growing because I didn't water it, or is it growing because of the sunlight? So experimental evidence must be carefully critiqued, meaning that we have to really think about the process by which we collected that evidence. What are the key questions as a researcher that you should consider when evaluating your results? Do you have good results? Did you put that plant out whenever it was just cloudy outside? It's winter and it's cold, but it's outside. It's still getting sunlight. So you need to be questioning everything you do in an experiment to see if that you are collecting quality evidence. So an example of this would be like whenever you guys were walking, doing the distance and displacement, some of us hit a wall and then we're like, oh no, what do we do? And then you walked around and then walked on the other side of the wall. Well, you're not accounting for some of that distance that you may not have been able to collect because there was a wall in your way. So is that good evidence? You as the experimenter get to decide. So when you are doing experiments, some good ideas, or even reading experimental results, some good ideas that you should be thinking about every time you read research. Is the experiment objective? Who is doing the research? Do they have a reason to be doing this research? A really good example of this would be there was a council that was put together by tobacco companies who were putting out information saying that cigarette smoke doesn't cause cancer in the 70s, 80s, something like that. Another thing that was being done is that energy companies were saying that burning fossil fuels wasn't impacting climate change, and that they were doing research on it, and it was actually good for the environment because plants need CO2. So when you're reading about this research and experiments that are being done, be critical. Ask who is doing the experiment. Do they have a reason for it? Do they have a reason to be honest? Next, could any other the variables have caused the observed effects? Once again, going back to the plant. If I left a plant out to get sunlight, but it's winter and it's dark outside, are those reliable? Could anything else have that I observed affect those plants? What plant was I using? Do they like sunlight? I don't know. Do other researchers observe the same result? Are we constantly, when we're doing these experiments and people before them, because once again, science is a cycle, are we getting the same results every single time? And has the data been analyzed to understand the uncertainties in measurement? Measurement is never perfect. It absolutely will never be perfect. My eyes may be better than your eyes. I may be better at weighing something than you. My instrument may be more specific and more calibrated than yours. There's always an uncertainty. Are scientists stating those uncertainties? One thing that you guys may be familiar with in seeing uncertainties is when they're doing polling information. When you're seeing there is an election this year. So whenever at the end of the election nights where they say that there's, a certain amount of uncertainty in the polling process, that's what they're talking about. Could there be an error? Where would it be? Okay. So all measured data, as I said before, contains some degree of uncertainty. This uncertainty or error is the unavoidable difference between a measurement and the true value. But if physics is based on measurement and all measurements contain uncertainty, then how can we be confident about scientific explanations based on experimental evidence? So I want you to brainstorm an answer to this question right now. Go ahead and pause, and once you're done, go ahead and hit play. So here's an example. Let's say that a student wants to test this scientific explanation that heavy objects will fall faster than lighter objects. So he drops a heavy stone and a light stone and collects this data on the time, how long it takes for it to fall, okay? The student argues that his data supports his explanation. His friend says he's wrong. What is the evidence for each view and who is right? Okay, so take a second now and answer these questions. Who is correct? And what evidence do they have for their claims? So what is the observed effect? What are we looking for here? We should see that the heavy rock should fall faster, because that was the claim. Are we seeing that in our times? What is the uncertainty in this data? What would cause the uncertainty? And is the observed effect significant compared to the uncertainty in the data? Do we see a huge difference between our conclusion here? So the heavy rock should be falling faster. Is it, according to our data? So this experiment does not support the explanation because the experiment finds no significant difference between them. Look, this is 0.78 seconds and this is 0.8. And the value on the heavy rock vary by more than 1/10 of a second, okay? It's not a huge difference. And the average value for both rocks by 1/200th of a second, okay? So we're not seeing, we're seeing vast uncertainty here, okay, between these measurements, but our conclusion should be the same, is that these numbers are really close. So uncertainty can never be eliminated. So what we need to do is we need to explain our measurement errors. We need to show that evidence must be evaluated. We need to look at that and see, can we trust these measurements? So how do you know a statement is true? We tend to argue the if-then statement. So if the Earth is round, then it should be possible to travel in the same direction and end back up at your starting place. So then we have to go through this whole process in order to determine if that's true or not. We have to find proposed potential consequences of the theory being true. Consequences in an observable test for the truth of the theory. If the consequences actually observed, the theory is supported. If the consequence is not observed, the theory is known to be at least partly incorrect. Okay, the whole thing might not be wrong, but part of it could be.